When you look at a chemical reaction doesn't just happen. You don't just combine X and Y and poof, it makes Z. It's all about making particles collide, and then those particles collide with other particles. It's actually a multi-step process. When you look at a chemical reaction, you're only seeing part of the picture. You're seeing the overall process, not all the steps that went into it. For instance, plants do this every day. They take carbon dioxide and water, they make sugar, glucose, and oxygen. But if we looked on the left-hand side, if all of this reaction happened in one step, you'd have 6 carbon dioxides hitting each other along with 6 waters, so that's 12 molecules all striking each other at exactly the right time with exactly the right orientation. That's never going to happen. It might be thermodynamically favorable, this one isn't, but even thermodynamically favorable reactions oftentimes have to be broken down into simple steps. So this is some vocabulary we'll use. An intermediate is just something where a chemical gets made in the middle of a reaction, some kind of chemical compound, and then it's used up in that same chemical compound. So somewhere along the way, something is made. You don't see it in the beginning, and you don't see it at the end. You only see it in the middle. Molecularity is a weird word that basically says how many particles had to collide in order for a reaction to occur. And an elementary step is just one of those simple steps. And once we have one of those simple steps, we can actually write a rate law just from an elementary step. For example, this is no and f makes noof. We can break down this top equation into these simple steps. If you notice, all we're doing is we're taking F2 right here and we're breaking the fluorines apart. So in the first step, we combine the NO2 with F, and in the second step, we take the remaining F and we combine it with the other O2. Notice that the 2 elementary steps add up to the overall equation. This is very important. The 2 steps must add up to the overall equation. In kinetics, we're always worried about how fast is the reaction going. We can look at the simple elementary steps and figure out which one the rate determining step is. Think about when your family goes somewhere. You can have all of you in the car except for that one slowest person in the house. That one slowest person in the house is going to determine when you leave. There's always one person that is the rate determining person. In chemistry, we have the same thing, rate determining steps. So let's take the elementary steps we had before and let's label them slow and fast. The slow step is the rate determining step. So we can write a rate law directly from that. So to write this rate law, all we do is write rate is equal to K. All we have to do is look at the slowest step. The slowest step is this one right here. Since we've identified the slowest step, in order to write the rate law, all we have to do is include the reactants of that slowest step. And now we have to figure out what the exponent of each one is. The easy part is the coefficient in front of each reactant is what you use as an exponent. In front of NO2 is a 1, and in front of F2 is a 1. Therefore, the rate law for this equation is K times NO2 times F2, both of them to the first power. Did you guys think, I think I see an intermediate? If you see the intermediate F, then you're right. F was made in the middle, and it was consumed in the middle. You don't see it at the beginning, and you don't see it at the end. F is an intermediate. Look over this chart and see if you can make some connections. Look down here. We have 2 things colliding, A and B. So it has a molecularity of 2, or bimolecular. The rate law is just A times B. Now shift focus down to here. This has a molecularity of 3, because we're combining 1 A particle and 2 B particles. We would call that trimolecular. And the rate law is got A times B squared. The squared comes from the fact that there's a 2 in front of the B. A catalyst works by changing the effect that orientation has on a chemical reaction. The important thing about a catalyst is it is not used up in a chemical reaction. It may disappear in the middle of it, but at the end, it comes back. I have a story about catalysts for you. Close your eyes. No, I said close your eyes. Okay. Go back in your mind to 7th grade, and in 7th grade, there is a young man named Joe. And Joe just loves Susie. He thinks that she is so cute and the hottest girl he has ever seen. Here's the problem though. Joe, being a very smart young man, is deathly afraid of women. So what's Joe to do? All Joe has to do is get up the nerve and go talk to Susie. Ain't never gonna happen. The activation energy is just too high. So how do we fix that problem? Luckily, in every 7th grade classroom is Pat. Pat is that person that's willing to go out and hand somebody a note and say, do you like me? Yes, no, or maybe so. Pat provides an alternate pathway, a pathway where Joe doesn't have to actually get up and go talk to Susie. Pat makes it easier for Joe to set up a relationship. Is Pat dating Joe? Is Pat dating Susie? No. Pat is not involved in the relationship and is free to then go put together other couples or pass on that note and split up couples. Because chemical reactions can often happen forward and backwards, and catalysts make both of those go faster, the forward reaction and the reverse reaction.
Open eyes now.
Enzymes, you may remember from biology, are just a catalyst, usually a protein, but sometimes RNA, that works in a biological system. You have an enzyme in you that allows you to break down starch and turn it into glucose. And it's made in your mouth, and it starts as soon as you put a piece of popcorn in your mouth. Go ahead and do it. You'll feel it start to dissolve and break down. You have a whole host of enzymes that allow you to take glucose, mix it with oxygen, and produce carbon dioxide and water. That is a thermodynamically favorable reaction. Then why doesn't sugar just react with oxygen out in the air? Because the activation energy is so high. The enzymes in your body allow that reaction to occur with less activation energy. Allow an alternate pathway so that less energy is needed to collide those particles and produce a reaction.